Now we turn to chapter 5, intertemporal choice. We've seen in the previous chapter many models for decision making under risk to incorporate all the behavioral findings to get more empirical realism. And you saw that more psychology came into the models, but also in a mathematical sense, the models became more difficult. We need more complex models. Similar things will happen in intertemporal choice, as we're going to see next. In fact, similar things happen in behavioral approaches for game theory, welfare theory, but we focus in this course, we don't have so much time, we focus on individual choice and then mostly for risk and time. So now we turn to intertemporal choice. First, I'm going to define decreasing impatience. You may remember that from decision under risk, the previous chapter, there was the certainty effect. That means people are attracted too much to a certain outcome. They like them more than maybe they rationally should. That was in fact underlying paradoxes such as the Allais paradox. In intertemporal choice, we have very similar, we have a presence effect. If people can get consumption right now, they like it really much, they like it a lot and too much. And that leads to same kind of irrationalities as with risky choice. And then decreasing impatience is quite analogous to the certainty effect. And I'm going to define now what that means. I'm going to start to simplify things a bit. We have already seen intertemporal choice with income streams. But to keep things simple from now on, we're going to assume there's only one non-zero outcome in that stream. In one time point, you get a non-zero outcome. And all the other time, it just gets zero. Zero means business as usual, nothing changes. So only one time point with the outcome to be discussed. And here's the notation. This means at time point t, you get outcome alpha, and all the other time points, zero. That means business as usual, status quo. A reason why we do this simplification is, you may remember when I presented the Koopman's theorem on discounted utility, I said there's a problematic condition, separability. For simplicity, people do it, but they know it's not so good. If we only look at dated outcomes, as we will do in the rest of this course, then separability, it can be seen that it never plays a role. So we avoid all those problems, those empirical problems and all these things. We keep things simple, and that's why we do it. I'm going to assume a functional representation of this multiplicative of this kind for these dated outcomes and preferences over them, where D is the discount function, U is the utility function, U is the assumptions, utility is continuous, strictly increasing, but now we do scale utility to be 0 at 0. And the reason is all the time points outside that time point T, we have status quo, so business as usual. We don't want to count them, and we should set utility to 0 there, then we can ignore them. So the scaling is now an important thing. The discount function also be continuous. It will be non-increasing. That's impatience. The farther away times are in the future, the less weight they have. So that is being impatient. We usually have normalization. The discount weight of the present is we put it to 1. That's just a matter of normalization to simplify things. The discounted model in the sense of constant discounted model, the classical model, has a discount function of this kind, a power function. You can always rewrite it as an exponential function, because here, just by that substitution. So the constant discounting, exponential discounting, that's the same thing. It implies stationarity. The theorem of Koopman's already said it. In fact, it will be homework for you to prove it. By impatience, the common empirical finding, I already told you, by impatience, it must be the case that delta is smaller than 1. Then the farther time is in the future, the less weight it has. So that's what impatience gives. Stationarity, you already saw the definition. You saw it for general income streams. Now we only have dated outcomes, only one non-zero outcome. I'm going to restate it for that special case. So stationarity, you will remember. And imagine here we have immediately right now, you get a sigma. Sigma means a small amount. And imagine if it's get delayed to some later time point L, then you want a somewhat bigger amount lambda to make it indifferent. So here the large money amount is exactly indifferent to the small soon amount, assume that. Then stationarity says if the consumption times are delayed, so the decision time remain the same right now, but the consumption times are delayed, then preference should not change. So we add the constant d, or we always take d positive. We added both to 0 and L. Indifference should remain the same. That was stationarity, you will remember. Anyway, so in words, I repeat it in words, but let's not read it again because you've seen it before. You can read it at home. A little bit I will generalize soon to come, but let me repeat the notation already said in words. We have a notation to have memory. S means the assumed time. In a moment ago, we took the assumed time to be 0, but we can have also the smallest time points, the assumed time can also be other than 0 in cases to come. Then we always have a later time denoted L, and we have L bigger than S. Then we have sigma, a small consumption coming soon. And we have lambda, a large consumption coming late usually, and lambda bigger than sigma. So this is notation that helps memory. That's why we use it. And usually implicitly d delay will be positive. Constant impatience, reformulating one more time now for general S, it says if at, before we saw S0, but now we do general S, if at some early time S, soon time small, is equivalent to somewhat later get lambda, then if we delay the consumption by d, nothing changes. In fact, so this seems to be more general because before we did it only for S is 0, but it is effective equivalent because stationarity means if this thing you move forward to the present, nothing changes. Stationarity means this thing you move forward to the present, nothing changes. By transitivity, they must be the same. So this is, it's just the same way to state constant impatience or stationarity as we had it before. Empirically, we don't find it. Empirically, we find violations. We find usually decreasing impatience, as it's called. That means if we start from the same preference here as here, and we delay by a positive d, then people become more patient, more willing to wait a bit for the big outcome. So you get this strict preference. Postponing consumption makes people more patient, more preferring the late, so to say. This is the prevailing empirical finding. And this is especially strong when S equals 0. So if the early time here is immediate consumption, people wait, they already feel the taste of the hamburger, whatever it is, they can't wait. And any delay, then it's delayed, they don't like it so much. So this effect is especially strong when the presence is involved. Then we call it the presence effect often. But also if the presence is not involved, still this is still the prevailing effect. What we've seen before, we've seen examples. For instance, maybe you remember what we discussed a few times. Right now, €100 or in 4 months, 105. And if the whole thing is delayed, the payment by 4 years, then preference reverse. Then here now you 4 years and 4 months, you're rather at 105 than this thing to the left. We've seen this many times before. That means right now you are impatient, but if we delay the consumption by 4 years, you are patient. So your impatience is decreasing. That is what these preferences show, decreasing impatience. But now the mathematicians among you will start protesting. They will say, wait a minute, you have to be precise. Decreasing impatience is defined as an indifference implying a strict preference. Formally speaking, we don't have it here. We don't start from an indifference. So formally speaking, you cannot call this decreasing impatience. That is what very precise mathematicians will say. But we can reassure them that this is correct what we say. And I'll do a little bit of work to show you that it is still correct what I do here. And to do that, what I'm going to do, and let me first write connotation. Let me write months, so 4 years plus 4 months, that's 52. So I wrote the same preference now in terms of months. Then I have these preferences. I want to get preference of that kind. How do I do it? I'm going to subtract some positive money amount, epsilon positive. I'm going to subtract it from this payment 100. I do so much, exactly so much that this turns into an indifference. And I'm assuming continuity, in this model. There's always a money amount between 100 and 0, such that we get, if you put it here, you get indifference. That's the first thing I do. That same money amount epsilon I subtract here also. Then here, of course, the preference only becomes stronger from it by doing it. So indeed, if I have these two preferences to start from, I can always turn them into these preferences. And then this is decreasing impatience, because if you look at these two, they are exactly of the form that it's above. An indifference by delay is turned into strict preference. So therefore, if I find a preference pattern of this kind, I can claim that I have decreasing impatience. Also mathematically, it's correct. Psychologically, you understand, but also mathematically, it is fully correct. It was an indirect way to get decreasing impatience. There's another, let me give you one more example of such reasoning. Imagine I start from the same preference as always, or indifference as I'm looking many times. So late, large, indifferent to immediate, small. Now the common delay is D, but imagine I get indifference if here this one I delay a bit more. The epsilon is going to be a positive number. Sorry, so epsilon is positive. Imagine I have these two indifferences. I'm claiming again that we have decreasing impatience. And again, the mathematician with protesters say you should have a strict preference. You don't have it, you have indifference. But I can always get it done. What I do, I simply remove the epsilon here. That means I'm moving this forward, come earlier. By strict impatience, you like it more. So you get strict preference of that kind. And then exactly we have, when I remove the epsilon here, you get the strict preference, then this is exactly of the form here. So if I start from two observations like this, again, I can claim that I have decreasing impatience. Also mathematically, it's correct. So these are kind of reasonings, good if you get used to. That's how we can work in intertemporal time, in intertemporal choice. So with these definitions refreshed and this basic empirical finding, deviating on a big category values from rationality models, deviating from stationarity, we know we have to search for new models that accommodate them, and that's coming now. And then you have to pull up your sleeve because the theoretical work is coming. That will be in the next recording.